Now that we have an understanding of mass, of matter, of energy, and how do these tie to each other through the two laws we looked before in the previous video, law of conservation of mass and law of conservation of energy, we are ready to ultimately, plow ahead with understanding what enthalpy really is. Now, for the uninitiated, enthalpy is a foreign word, as it is to me. Enthalpy could be denoted by, well, it's nothing but, as I mentioned before, a change in energy. A change could be denoted by the Greek symbol delta. And it's nothing but the change of energy. So it's delta energy. Now you may be asking, well, change of energy of what? Of course, chemical reactions. But before we move on with understanding enthalpy, we must fixate our eyes on what types of energy would any substance contain. So I have a substance, and the substance will have fundamental particles, atoms in form of compounds and elements. Every atom has energy. Now let's think of an atom. Well, you have a nucleus, and you would be having electrons flowing around the nucleus, and in their respective orbitals. So say this was oxygen atom, so you would have oxygen with its electrons in the middle over here. So you have in the nucleus you have the protons, which are positively charged, plus you have neutrons, which are neutral. Now, of course, these protons and neutrons are to be held together. There must be a force holding these together, and they are called strong forces. Well, that's what physicists call it, strong forces. And around the nucleus you have electrons flowing around. Now, the electrons will have kinetic energy because they are buzzing around. They're going from here. Imagine this electron started from this point. It's going, it's going below. It's going, then it's going above again. Okay, I sound silly, I know. But essentially, you understand what I'm saying. The electrons are moving. Hence, they have kinetic energy. Much like if you are moving in a vehicle, your vehicle has energy, or you walking would, if you're walking, your body would have kinetic energy. So that body of electrons, each electron has a certain amount of kinetic energy. That's important to understand. The nucleus has strong forces holding together protons and neutrons. That would be the amount of potential energy. Not only that, you have to, if we further go up the resolution, let's escape the atom and let's see how different atoms would interact in a molecule. Let's draw a molecule. And this molecule, say, would have, say if this molecule were to be, let's call it for the sake of clarity, CO2, you would have in CO2, what atoms would you have in CO2? I should ask you that question. You would have CO2, so you would have oxygen, O2, so you would have oxygen molecules. Just oxygen molecules, and you would have a proportional amount of carbon molecules. Okay, my apologies. You would have oxygen atoms. You would have oxygen atoms and you would have carbon atoms. Now you would now in a compound of CO2, you would have many CO2 molecules. Many. Say if you had 2 moles of CO2, then if you had 2 moles of CO2, you would have 6 times 10 to the power 23 multiplied by 2, because that many particles are there in a mole. You'd have that many number of CO2 molecules. Now, if there are so many CO2 molecules, there must be the interaction between these molecules. These molecules would be vibrating. So if you have one CO2 molecule here, you have one CO2 molecule here, another here, another here. These molecules are vibrating constantly. And as we know, the faster they vibrate, the more hot they appear. They're vibrating. Not only they're vibrating in different directions. They're vibrating in linear ways. They are vibrating in longitudinal ways, or you can say longitudinal waves. Longitudinal. Not only that, there are also torsional forces, and by torsional I mean, well, an easier way to understand torsional forces would be, say you have say you had a bottle. Now it looks well, you know, this looks like my mother's perfume bottle, and surprisingly it's a plastic bottle. Now if you were to grab this plastic bottle, and if you were to twist it in this direction, what would you have? You would be twisting the bottle, and the forces would be going this way. So you're not stretching the bottle, neither are you trying to shrink the bottle. You are twisting it, and hence the word, or hence the force type comes this force type called torsional forces. The molecules are vibrating in 3 ways. We have seen the nucleus having strong forces holding them together. We also know the electrons are moving and they have kinetic energy. Not only that, you also have to understand these molecules would be attracting each other. Well, CO2 is a non-polar molecule, but we'll not get into too much details, because aside these forces, we also have other forces to consider. The first type being intermolecular forces. And not only that, the fact that, you know, you have one carbon atom joined with 2 other oxygen atoms means you have these bonds over here. And what are these bonds? These bonds are nothing but they are intramolecular forces. Now again, it's easy to remember if you think about inter being between 2 objects. So if you had one CO2 molecule, inter would be the force of attraction between these 2. Now if you had intra, which means within something, intra, it would be the forces existing within forces existing within the CO2 molecule itself, and the forces would be these bonds over here. And what do we know about chemical bonds? Chemical bonds are nothing but electrons being shared between 2 atoms. Well, that's not always the case, because these are covalent bonds. You could have ionic bonds and so many other types of bonds. But in this example, with covalent bonds, which are intramolecular forces, they will house a certain amount of potential energy. And one good example of potential energy being released from these bonds, a simpler one would be, say, the combustion of methane. Now I have CH4, which is methane, and methane is often, due to having one carbon and its intermolecular forces being low, it's often found in gaseous state. In standard room temperature and pressure. We'll get into further how standard room temperature pressure ties in with enthalpy calculations later on. But over here, moving back to combustion of methane, we have CH4. We combust that with oxygen, because oxygen is required to combust any material. What do we see? We would have, as you know, the products of combustion. The products of combustion are CO2, which would be in its gaseous state in room temperature and pressure. And you would be having water, H2O. That's if we have a complete combustion. If it was incomplete, then you would have another additional component, such as carbon monoxide. But this is complete, so that's not relevant.